Welcome to Dreamy Facts. As the day gently recedes, we invite you to settle into a space of calm contemplation. Tonight, we embark on a journey through the ocean, exploring approximately 100 fascinating facts that reveal intricate patterns, subtle wisdom, and profound beauty within its vast, shimmering depths. There is no pressure to remember or retain these details. Instead, let them unfold naturally, inviting your mind to settle into a state of peaceful curiosity. This exploration is designed to be a soothing experience, a gentle current of knowledge flowing without demanding effort or retention. We will observe the intricate dance of marine life, the subtle adaptations of ecosystems, and the quiet wisdom embedded in the ocean's ancient rhythms. Each fact is a small window into the vast and interconnected tapestry of the ocean, presented in a calm and meditative tone, allowing your thoughts to drift and find stillness. Allow the gentle rhythm of these discoveries to guide you towards a state of relaxation, inviting a sense of wonder and peace as you prepare for rest. If you're finding peace in this journey, a like and subscribe helps us continue creating these restful explorations, and we're always curious. Share in the comments what city and time zone you're watching from. There's something special about knowing this experience is reaching people all over the world as they prepare for rest. As we begin our journey into the profound mysteries of the ocean, we first turn our attention to its sheer scale, its immense presence on our planet. We contemplate the vastness that covers so much of Earth, a realm of incredible depths and expansive waters, holding secrets within its silent embrace. The ocean's vastness. The ocean is a dominant feature of Earth, covering approximately 71% of the planet's surface. This immense body of water holds about 97% of all water on Earth, making it a critical component of our global climate and ecosystems. Scientists have observed that the volume of the ocean is so vast that if all land masses were flattened, the entire planet would be covered by a layer of water nearly 3 kilometers deep. This illustrates the overwhelming scale of the marine environment compared to terrestrial habitats. Research shows that the 5 major ocean basins, the Pacific, Atlantic, Indian, Southern, Antarctic, and Arctic, are all interconnected, forming a single global ocean that flows continuously around the continents. This interconnectedness allows for the global distribution of heat, nutrients, and marine species, shaping weather patterns and supporting diverse forms of life across vast distances. Current understanding suggests that the ocean's surface area is roughly 361 million square kilometers, a staggering figure that hints at the endless possibilities for discovery within its bounds. Average depth and volume. While the ocean covers a vast area, its depth is equally impressive, contributing significantly to its overall volume. The average depth of the world's ocean is approximately 3,188 meters, 12,100 feet. To put this into perspective, if Mount Everest, the tallest mountain on land, were placed in the deepest part of the ocean, its peak would still be submerged by over 2 kilometers of water. This immense average depth indicates that the majority of the ocean exists in conditions of perpetual darkness and extreme pressure. Studies indicate that the total volume of the ocean is estimated to be around 1.35 billion cubic kilometers, a figure that is almost incomprehensibly large. This vast volume of water acts as a massive heat sink, absorbing and distributing solar energy, which plays a crucial role in regulating Earth's temperature and climate. Scientists have observed that this thermal regulation helps to stabilize global temperatures, preventing extreme fluctuations that would otherwise make the planet inhospitable to life. The sheer scale of the ocean's depth and volume underscores its profound influence on planetary processes. The Mariana Trench and Challenger Deep. Delving into the ocean's most extreme points, we encounter the Mariana Trench, located in the western Pacific Ocean. This colossal canyon in the seafloor is the deepest known point on Earth, a testament to the planet's geological forces. Within the Mariana Trench lies the Challenger Deep, which reaches an astonishing depth of approximately 10,129 meters, 35,156 feet. At this profound depth, the pressure is immense, exceeding 1,000 times the atmospheric pressure at sea level. Research shows that this pressure is equivalent to having 50 jumbo jets stacked on top of you, yet life still thrives in these seemingly impossible conditions. Scientists have observed unique species of fish, crustaceans, and microorganisms that have evolved specialized adaptations to survive the crushing forces and perpetual darkness. These include amphipods, which are tiny shrimp-like creatures, and various types of sea cucumbers. The exploration of Challenger Deep, first achieved by the bathyscaphe Trieste in 1960, and later by remotely operated vehicles and even solo human descents, continues to reveal the incredible resilience of life. The Hadal Zone. Beyond the abyssal plains, the ocean plunges further into what scientists refer to as the Hadal Zone. This zone encompasses the deepest trenches and troughs, extending from approximately 6,000 meters, 20,000 feet, down to the ocean's deepest points. It is named after Hades, the Greek god of the underworld, perfectly reflecting its dark and extreme nature. The Hadal Zone represents less than 2% of the total ocean area, yet it accounts for the deepest 45% of the ocean's depth range. Studies indicate that despite the extreme pressure, lack of light, and scarce food resources, the Hadal Zone supports a unique and surprisingly diverse array of life, primarily invertebrates such as amphipods, sea cucumbers, and specialized polychaetes, bristleworms. These organisms have evolved specific biological and physiological mechanisms to cope with the intense conditions, including pressure-resistant proteins and cell membranes. Current understanding suggests that organic matter reaching these depths often arrives as, quote, falling detritus from shallower waters, providing a crucial food source for the benthic communities. The Hadal Zone remains one of the least explored environments on Earth, a frontier of discovery. Ocean basins and mid-ocean ridges. The vast floor of the ocean is not a flat, featureless expanse, but is characterized by complex geological structures, including immense ocean basins and towering mid-ocean ridges. Ocean basins are large depressions in the Earth's surface that are filled with seawater, encompassing abyssal plains, trenches, and continental margins. Research shows that these basins are formed through the process of plate tectonics, where oceanic crust is created at mid-ocean ridges and consumed at subduction zones. Mid-ocean ridges are underwater mountain ranges that span tens of thousands of kilometers across the globe, forming the longest mountain chain on Earth. The Mid-Atlantic Ridge, for example, runs down the center of the Atlantic Ocean, where new oceanic crust is continuously generated as tectonic plates pull apart. Scientists have observed that these ridges are sites of significant geological activity, including volcanic eruptions and hydrothermal venting. These processes not only shape the sea floor, but also play a critical role in the chemical composition of seawater and the cycling of elements globally. Hydrothermal vents, oases of life. Amidst the cold, dark depths of the ocean floor, hydrothermal vents emerge as vibrant oases of life, challenging our traditional understanding of energy sources for ecosystems. These vents are fissures in the seafloor from which geothermally heated water, rich in dissolved minerals, streams out. Research shows that the water discharge from these vents can reach temperatures exceeding 400 degrees Celsius, 750 degrees Fahrenheit, though it does not boil due to the immense pressure at these depths. Unlike most ecosystems on Earth that rely on sunlight for energy through photosynthesis, the communities around hydrothermal vents thrive on chemosynthesis. Specialized bacteria convert hydrogen sulfide and other chemicals from the vent fluids into organic matter, forming the base of a unique food web. Scientists have observed an astonishing array of life around these vents, including giant tube worms, which can grow over 2 meters long, as well as unique species of clams, mussels, shrimp, and crabs. These organisms have adapted to extreme conditions, including high temperatures, toxic chemicals, and complete darkness, showcasing the incredible resilience and adaptability of life on Earth. The discovery of hydrothermal vents in 1977 revolutionized our understanding of deep-sea biology and the potential for life in extreme environments. Seamounts and guyots. Rising majestically from the abyssal plains are seamounts and guyots, underwater mountains that do not break the surface of the ocean. Seamounts are typically volcanic in origin, formed by eruptions on the seafloor. They vary widely in size, but are generally defined as features rising at least 1,000 meters, 3,280 feet, above the seafloor. Research indicates there are tens of thousands of seamounts globally, though only a fraction have been thoroughly mapped or explored. Guyots are a specific type of seamount characterized by a flat top, which suggests they were once islands that were eroded by wave action before subsiding below the sea surface. Scientists have observed that seamounts act as biodiversity hotspots, attracting a rich array of marine life, including deep-sea corals, sponges, and various fish species. Their steep slopes and varied topography create complex habitats and generate localized currents that bring nutrient-rich waters from the depths. This concentration of life makes seamounts crucial areas for marine biodiversity and often significant fishing grounds, though their ecosystems are fragile and vulnerable to human impacts. The study of seamounts provides valuable insights into oceanic geology and the distribution of deep-sea species, as we gently drift from the silent majesty of seamounts and guyots, those hidden peaks and plateaus that punctuate the abyssal plains, we begin to turn our attention upward, through the vast column of water itself. Imagine, if you will, the sheer volume of this liquid realm, the very substance that fills the basins and cradles the deep-sea mountains we've just explored. It is this water, with its unique properties and ceaseless motion, that truly defines the ocean, shaping life within it, and influencing the very breath of our planet. We invite you now to settle deeper into your tranquil space, allowing your thoughts to flow with the gentle current of knowledge as we explore the fundamental characteristics of ocean water. the ocean's salty essence. The most defining characteristic of ocean water is perhaps its salinity. We often perceive the ocean as simply salty, but the science behind this taste is remarkably intricate. Research shows that on average, a kilogram of seawater contains about 35 grams of dissolved salts. This is typically expressed as 35 parts per thousand, send to zero, or 3.5%. These salts are not just common table salt, sodium chloride, but a complex cocktail of various dissolved minerals, including magnesium, sulfate, calcium, and potassium, among others. Where do these salts come from? Scientists have observed that the primary sources are the weathering and erosion of rocks on land, carried by rivers to the sea, and volcanic activity, both on land and beneath the waves, which releases minerals directly into the water. Over eons, as water evaporates from the ocean's surface, leaving the salts behind, and then returns as freshwater rain, the concentration of these dissolved solids has steadily increased, creating the briny solution we know today. This constant cycle ensures the ocean remains a vast saline reservoir. Salinity varies across the globe. While 3.5% is the average, the ocean's salinity is not uniform. We find fascinating variations depending on location. For instance, in areas with high evaporation rates and low freshwater input, such as the Red Sea or the Persian Gulf, salinity can soar to over 40%. Conversely, near the mouths of large rivers, where vast quantities of freshwater pour into the ocean, or in polar regions where melting ice dilutes the surface water, salinity can drop significantly, sometimes as low as 20%. These subtle differences in salt concentration play a crucial role in creating density gradients, which in turn drive some of the most powerful currents on Earth: temperature stratification and the thermocline. As we consider the water column, we encounter another fundamental property: temperature. The ocean is not a uniformly cold body of water, rather it is exquisitely stratified. Near the surface, the sun's warmth penetrates, creating a relatively warm mixed layer, but as we descend, we experience a dramatic shift. Studies indicate that a distinct boundary, known as the thermocline, exist in many parts of the ocean. This is a layer where temperature rapidly decreases with increasing depth. Below the thermocline, in the vast deep ocean, temperatures are consistently cold, typically ranging from 0 to 4 degrees Celsius, 32 to 39 degrees Fahrenheit. This stratification, this layering of warm over cold, acts as a significant barrier, influencing the distribution of marine life and the movement of nutrients, the ocean as a global thermostat. The immense volume of ocean water, with its high specific heat capacity, allows it to absorb and store vast amounts of solar energy. This makes the ocean an unparalleled global thermostat. We observe that it absorbs about a quarter of the carbon dioxide released by human activities and has absorbed over 90% of the excess heat generated by global warming since the 1970s. Without this incredible capacity, our planet's surface temperatures would be far more extreme and volatile. The ocean's ability to slowly release this stored heat back into the atmosphere over time profoundly influences global weather patterns and climate systems, shaping the very air we breathe and the seasons we experience. Density, the engine of deep ocean currents. The interplay of temperature and salinity determines the density of seawater. a critical factor in driving the ocean's deepest currents. Colder water is denser than warmer water, and saltier water is denser than fresher water. We can imagine these differences creating invisible hills and valleys of density. When cold, salty water forms, often in the polar regions, it becomes incredibly dense and sinks, initiating a slow but powerful journey across the ocean floor. This process is the very engine of the thermohaline circulation, a vast global conveyor belt that we will explore further. It is a testament to the subtle wisdom of the ocean that such seemingly small differences can orchestrate such monumental movements. The invisible weight of pressure. Returning to the concept of depth, we must revisit the profound impact of pressure. As we descend into the ocean's depths, the weight of the water above us increases dramatically. For every 10 meters, approximately 33 feet, we go down, the pressure increases by about 1 atmosphere, or 14.7 pounds per square inch. This means that at the average ocean depth of 3,688 meters, the pressure is roughly 370 times that at the surface. In the Challenger Deep, it's equivalent to about 50 jumbo jets piled on top of you. How can life exist under such immense force? Scientists have observed that deep-sea organisms have evolved extraordinary adaptations. Their bodies often lack air-filled spaces that would collapse, and their cellular structures and enzymes function optimally under these extreme conditions. Some even use osmolytes, organic compounds that protect proteins from denaturation, allowing them to thrive in environments that would instantly crush most surface dwellers. This is a profound example of life's resilience and adaptability. The photic zone, where light sustains life. As we ascend back towards the surface, we encounter the crucial boundary where sunlight penetrates. The aphotic zone, also known as the euphotic zone, is the uppermost layer of the ocean where there is enough sunlight for photosynthesis to occur. Its depth varies greatly depending on water clarity and the angle of the sun, ranging from a few meters in turbid coastal waters to over 200 meters, about 660 feet, in clear, open ocean. This sunlit zone is the vibrant engine of marine life. Here, microscopic phytoplankton, the ocean's primary producers, convert sunlight into energy, forming the base of nearly all marine food webs. We can think of this as the ocean's green pasture, feeding everything from tiny zooplankton to the largest whales. The vast majority of marine biodiversity, both in terms of species numbers and biomass, resides within this relatively thin, sun-drenched layer. The aphotic zone, a realm of darkness. Below the photic zone lies the vast, eternally dark aphotic zone. Here, sunlight cannot penetrate and photosynthesis is impossible. This realm, encompassing the mesopelagic, twilight zone, bathypelagic, midnight zone, abyssopelagic, abyssal zone, and hadalpelagic, hadal zone layers, relies entirely on organic matter raining down from the sunlit surface, the marine snow we touched upon in the previous chapter, or from chemosynthetic processes near hydrothermal vents. Life in the aphotic zone is a testament to ingenious adaptation. Many creatures here have evolved bioluminescence, producing their own light for hunting, attracting mates, or evading predators. Others have extremely large eyes to capture the faintest glimmer of light, or have lost their eyesight entirely, relying instead on highly developed senses of smell, touch, and pressure detection. It is a world of silent hunters and patient waits, a reminder of the incredible diversity of strategies life employs to survive in the absence of light. Ocean currents, the planet's circulatory system. With an understanding of water's properties, we can now appreciate the dynamic forces that drive ocean currents, the massive, continuous movements of seawater that crisscross the globe. We can envision these currents as the planet's circulatory system, distributing heat, nutrients, and marine organisms across vast distances. They are broadly categorized into surface currents and deep ocean currents, each driven by different yet interconnected mechanisms. Surface currents are primarily wind-driven. The most visible and often fastest currents are those at the ocean's surface. Studies indicate that these currents are primarily driven by global wind patterns, which drag on the water's surface, creating friction and setting the upper layers into motion. The Earth's rotation, through the Coriolis effect, then deflects these moving waters, curving their paths clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. This interplay of wind and rotation creates vast circular current systems known as gyres. The North Atlantic gyre, for example, includes the powerful Gulf Stream, which carries warm water from the tropics northeastward, profoundly influencing the climate of Western Europe. These surface currents are not just pathways for water, they are vital conduits for marine life, transporting larvae, nutrients, and even pollutants across entire ocean basins. The global conveyor belt, thermohaline circulation. Beneath the wind-driven surface currents lies a much slower but equally powerful system of deep ocean currents known as the thermohaline circulation. We refer to it as the global conveyor belt because it effectively connects all the world's oceans in a continuous, albeit incredibly slow loop. This circulation is driven by differences in water density, which, as we discussed, are influenced by temperature, thermo, and salinity, haline. Current understanding suggests that this process begins in polar regions, particularly in the North Atlantic and around Antarctica. Here, cold temperatures and the formation of sea ice, which leaves salt behind in the remaining water, create extremely cold, salty, and therefore dense water. This dense water sinks to the ocean floor and begins its long, slow journey across the abyssal plains, spreading throughout the global ocean. The speed and scale of the conveyor belt. Unlike surface currents that can move at several miles per hour, the deep ocean currents of the thermohaline circulation move at a glacial pace, often just centimeters per second or a few miles per year. To put this into perspective, a parcel of water sinking in the North Atlantic might take hundreds, even 1,000 years to complete its journey around the globe and return to the surface. Despite its slowness, the sheer volume of water involved is staggering. This massive, invisible river in the deep ocean plays an indispensable role in regulating Earth's climate by transporting vast quantities of heat, oxygen, and nutrients around the planet. It is a testament to the ocean's immense scale that such a slow process can have such profound global impacts. Upwelling, bringing life from the deep. While the deep ocean currents are a slow global movement, localized vertical movements of water are equally vital. One such phenomenon is upwelling, where cold, nutrient-rich water from the deep ocean rises to the surface. We often observe upwelling occurring along coastlines where prevailing winds push surface waters away from the shore, or in areas where ocean currents diverge. This process is incredibly important for marine ecosystems. The deep ocean, largely devoid of sunlight, accumulates decomposed organic matter, making its waters rich in essential nutrients like nitrates and phosphates. When these waters are brought to the surface, they fertilize the photic zone, leading to explosive growth of phytoplankton. Consequently, upwelling zones are among the most productive and biodiverse areas in the ocean, supporting vast fisheries and attracting a wide array of marine life. Downwelling, carrying oxygen to the depths. Conversely, downwelling occurs when surface water sinks, carrying oxygen and warmth to deeper layers. This typically happens in areas where surface waters become denser, either due to cooling or increased salinity, or where winds push surface waters towards the coast, forcing them downwards. While not as directly linked to primary productivity as upwelling, downwelling is crucial for aerating the deep ocean. It ensures that oxygen, produced at the surface by photosynthesis and absorbed from the atmosphere, is transported to the abyssal and hadal zones, making life possible for the deep-sea organisms we discussed earlier. Without this continuous replenishment, the deep ocean would become an anoxic wasteland, incapable of supporting complex life. Waves, the ocean's rhythmic breath. Shifting our focus to the more immediate and observable dynamics, we encounter waves, the ocean's rhythmic breath. We often think of waves as the crashing breakers on a beach, but they are a far more complex phenomenon. Essentially, waves are disturbances that transfer energy through water, not the water itself. Imagine a ripple in a pond. The water moves up and down, but the disturbance travels across the surface. Most ocean waves are generated by wind blowing over the water's surface. The stronger the wind, the longer it blows, and the greater the distance, fetch, over which it blows, the larger the waves will be. Once generated, waves can travel vast distances across entire ocean basins, often organizing into long, smooth swells that carry the energy from distant storms to faraway shores. The anatomy of a wave. Let's take a moment to appreciate the simple elegance of a wave structure. We can identify several key components. The yaw cresti is the highest point of the wave, and the yad trough is the lowest. The vertical distance between a crest and a trough is the wave height, while the horizontal distance between two consecutive crests or troughs is the wavelength. The time it takes for two consecutive crests to pass a fixed point is the wave period. These measurements help scientists understand and predict wave behavior, crucial for navigation, coastal engineering, and even understanding climate patterns. Tides, the ocean's gravitational dance. Beyond wind-driven waves, the ocean experiences another powerful rhythmic movement: tides. We observe the rise and fall of sea levels twice a day in most coastal areas, a phenomenon driven by the gravitational pull of the moon and, to a lesser extent, the sun. The moon's gravity pulls on the Earth and its oceans, creating bulges of water on both the side of Earth closest to the moon and on the opposite side. As the Earth rotates through these bulges, coastal areas experience high tides. In the regions between the bulges, where the water is drawn away, low tides occur. This celestial dance is a constant, predictable force shaping coastlines, influencing marine life in intertidal zones, and even playing a role in the mixing of coastal waters. Spring tides and neap tides. The alignment of the moon and sun creates variations in tidal range. Current understanding suggests that when the sun, moon, and earth are aligned, during new moons and full moons, their gravitational pulls combine, resulting in exceptionally high tides and very low tides. These are known as spring tides, named not for the season, but from the German springen, meaning to spring forth. Conversely, when the sun and moon are at right angles to each other relative to Earth, during the quarter moons, their gravitational forces work against each other. This results in less extreme tides, with lower high tides and higher low tides, known as neap tides. These cyclical variations are a beautiful demonstration of celestial mechanics at play in our oceans. Dissolved gases, the ocean's breath. Just as we breathe air, the ocean. Quote 5. Dissolved gases. The most critical of these for marine life is oxygen, which is essential for the respiration of almost all marine organisms. We find that oxygen enters the ocean primarily through two mechanisms: absorption from the atmosphere at the surface, where waves and turbulence enhance gas exchange, and as a byproduct of photosynthesis by phytoplankton in the photic zone. The concentration of dissolved oxygen varies with depth, temperature, and biological activity. It is generally highest at the surface and in cold, well-mixed waters. As we descend into the deep ocean, oxygen levels can decrease significantly, especially in areas with sluggish circulation or high organic decomposition, leading to what are known as oxygen minimum zones. The ocean as a carbon sink. Another vital dissolved gas is carbon dioxide, CO2. The ocean is a massive carbon sink, absorbing a significant portion of the CO2 from the atmosphere. This absorption occurs through direct gas exchange at the surface and through biological processes where marine organisms use CO2 for photosynthesis and to build shells and skeletons. This capacity has historically helped regulate Earth's climate by buffering atmospheric CO2 levels. However, as human activities release ever-increasing amounts of CO2, the ocean's absorption capacity is being stretched. Research shows that this excess absorption is leading to ocean acidification, a phenomenon where the pH of seawater is decreasing, with profound implications for marine ecosystems, particularly those organisms that rely on calcium carbonate to build their shells and skeletons. This gentle, calming journey reminds us not only of the ocean's wonders but also of its delicate balance. We invite you to let these facts about the ocean's very essence, its salinity, temperature, density, and dynamic movements, wash over you. The intricate dance of its waters, driven by unseen forces and supporting countless lives, is a profound testament to the interconnectedness of our planet. Allow this sense of wonder to deepen your peaceful contemplation as we continue our exploration into the vast, shimmering depths. As we gently drift through the foundational truths of our ocean, understanding its immense structures and the intricate dance of its waters, a new vista unfolds before us. We now turn our gaze to the most breathtaking aspect of this blue realm, the life it cradles within its vast, shimmering depths. Imagine, if you will, the sheer abundance, the vibrant spectrum of existence that calls this fluid world home. we invite you to contemplate the incredible biodiversity, the myriad forms and functions, the countless stories of survival and beauty woven into the ocean's very fabric. Research shows that the ocean is a cradle of life, hosting an estimated 50 to 80% of all life on Earth, much of which remains undiscovered and unexplored. This staggering statistic underscores the profound mystery and the immense biological richness that lies beneath the surface. From the microscopic to the colossal, every niche, every current, every corner of the ocean teems with beings uniquely adapted to their environment, forming an intricate, interdependent web of life. At the very base of nearly all marine food webs, and indeed much of life on Earth, are the often unseen heroes. Plankton. We speak of two primary types, each playing an indispensable role. Phytoplankton. The plant-like plankton are microscopic organisms that drift near the ocean's surface, within the sunlit photic zone. These tiny powerhouses perform photosynthesis, converting sunlight into energy, much like terrestrial plants. They are responsible for producing at least half of the oxygen we breathe, a truly astonishing contribution from organisms invisible to the naked eye. Imagine, with every breath you take, you're connected to these minute drifting green cells, silently toiling in the sun-drenched upper layers of the ocean. They are not merely oxygen producers. They are the primary producers of energy, forming the crucial foundation upon which almost all other marine life depends. Then there are the zooplankton, the animal-like plankton. These tiny creatures, ranging from microscopic protozoans to small crustaceans like copepods and krill, graze on phytoplankton. They are the vital link, transferring the energy captured by phytoplankton up the food chain to larger organisms. Think of krill, for instance, a type of zooplankton that forms vast swarms in polar waters, providing the primary food source for baleen whales, seals, and penguins. The sheer biomass of plankton is immense, a living, breathing, photosynthesizing, and consuming cloud that underpins the entire ocean ecosystem, regulating global cycles and shaping the very atmosphere we inhabit. Scientists have observed that even slight changes in plankton populations can have cascading effects throughout the marine world, underscoring their critical yet fragile importance. Moving beyond these foundational organisms, we encounter some of the ocean's most vibrant and complex ecosystems, often referred to as the rainforests of the sea. Coral reefs. These stunning underwater cities are built by tiny animals called coral polyps, which secrete calcium carbonate to form hard, stony skeletons. Over millennia, these skeletons accumulate, creating elaborate three-dimensional structures that provide shelter, food, and breeding grounds for an astounding diversity of marine life. Studies indicate that coral reefs, while covering less than 1% of the ocean floor, support over 25% of all marine species. The secret to their vibrant success lies in a remarkable symbiotic relationship. Inside the tissues of many coral polyps live microscopic algae called zooxanthellae. These algae perform photosynthesis, providing the coral with up to 90% of its energy, while the coral, in turn, offers the algae a protected environment and compounds necessary for photosynthesis. This delicate partnership is what gives corals their brilliant colours and allows them to thrive in nutrient-poor tropical waters. However, This symbiosis is incredibly sensitive to environmental changes. Rising ocean temperatures, a consequence of global warming, can cause corals to expel their zooxanthellae, leading to coral bleaching, where the corals turn white and often die if conditions do not improve. This, along with ocean acidification, pollution and overfishing, represents a significant threat to these invaluable ecosystems, reminding us of the profound impact of human activity on the ocean's delicate balance. Beyond the sun-drenched warm waters of coral reefs, other highly productive ecosystems flourish. In cooler, temperate regions, we find majestic kelp forests. These underwater forests are formed by large brown algae that can grow rapidly, sometimes over a foot a day, reaching heights of over 100 feet. Like terrestrial forests, kelp provides a complex habitat, offering shelter and food for a diverse array of fish, invertebrates, and marine mammals, including sea otters, which play a crucial role in maintaining the health of these ecosystems by preying on kelp-eating sea urchins. The towering fronds create a dynamic, swaying environment, a sanctuary teeming with life, and a vital carbon sink. Along coastlines, particularly in tropical and subtropical regions, mangrove forests and seagrass beds form critical transitional ecosystems. Mangroves are unique trees and shrubs that thrive in brackish water, their intricate root systems creating sheltered nurseries for juvenile fish and crustaceans, while also protecting coastlines from erosion and storm surges. They are incredibly efficient carbon sinks, storing vast amounts of carbon in their soils. Seagrass beds, on the other hand, are flowering plants that grow in shallow, calm coastal waters. They stabilize sediments, filter pollutants, and provide essential foraging grounds for marine turtles, manatees, and countless fish species. Both mangroves and seagrass beds are vital carbon sequesters and biodiversity hotspots, yet they too face significant threats from coastal development, pollution, and climate change. As we descend deeper, leaving the sunlit embrace of the photic zone behind, we enter the vast, dark expanse of the aphotic zone, where life adapts to perpetual twilight or absolute darkness. Here, the pressures are immense, temperatures are near freezing, and food is scarce. Yet, life persists, exhibiting some of the most extraordinary adaptations on Earth. We have already touched upon bioluminescence, but in the deep sea, it becomes a primary mode of communication, hunting, and defense. Many deep-sea creatures, from anglerfish with their glowing lures to shimmering jellyfish, use their own light to attract mates, lure prey, or startle predators in a world devoid of sunlight. The deep sea also showcases phenomena like deep-sea gigantism, where some invertebrates such as giant squid, colossal isopods, and enormous amphipods grow to sizes far exceeding their shallow water relatives. Scientists hypothesize that this could be due to colder temperatures, slower metabolisms, and reduced predation pressure in the deep, allowing for longer lifespans and continuous growth. Food, often arriving as marine snow, a continuous shower of organic detritus falling from the upper ocean, is a precious commodity. Creatures here are often opportunistic feeders, with large mouths, expandable stomachs, and slow metabolisms designed to conserve energy between infrequent meals. And then there are the remarkable ecosystems we explored in the previous chapter, centered around hydrothermal vents. Here, life thrives not on sunlight, but on chemosynthesis, a process where specialized bacteria convert chemicals from the Earth's interior, like hydrogen sulfide, into energy. These bacteria form the base of an entirely unique food web, supporting communities of bizarre and wonderful creatures, including giant tube worms, blind shrimp, and unique mussels and clams. These oases of life, discovered only in the late 1970s, completely revolutionized our understanding of where and how life could exist, proving that sunlight is not the only ultimate source of energy for complex ecosystems. The interconnectedness of marine life is a fundamental principle, forming intricate food webs that span the entire water column and across vast distances. Energy flows from the primary producers, phytoplankton in the sunlit zone, chemosynthetic bacteria in the deep, up through various levels of consumers. Zooplankton graze on phytoplankton, small fish eat zooplankton, larger fish and marine mammals prey on smaller fish, and so on. Even after death, organisms contribute to the cycle, their remains sinking to fuel scavenger and decomposer communities in the deep. This constant flow of energy and nutrients highlights the delicate balance of the ocean's ecosystems, where the removal or decline of one species can have ripple effects throughout the entire web. From the smallest, most ephemeral plankton to the largest, most majestic marine mammals, the ocean is a testament to evolution's boundless creativity. Consider the marine mammals. Whales, dolphins, seals, manatees, sea otters. These warm-blooded creatures have made incredible adaptations to life in the water, developing streamlined bodies, blubber for insulation, specialized lungs for deep diving, and sophisticated communication systems like echolocation. Their presence at the top of many marine food webs underscores the health and productivity of the ecosystems below. Similarly, the sheer diversity of fish species, from the vibrant inhabitants of coral reefs to the bizarre forms of the deep sea, showcases an astonishing range of shapes, sizes, and survival strategies. However, as we marvel at this incredible tapestry of life, we are also confronted with the profound challenges it faces. Beyond ocean acidification, which we explored in the previous chapter, marine biodiversity is under increasing threat from a multitude of human activities. Overfishing has depleted fish stocks globally, disrupting food webs and impacting the livelihoods of millions. Pollution, particularly from plastics, chokes marine life and contaminates habitats, with microplastics now found in every corner of the ocean, even within the deepest trenches. Habitat destruction. Driven by coastal development, destructive fishing practices and climate change further diminishes the critical spaces where marine life can thrive. Understanding these threats is not meant to diminish the peaceful wonder of our exploration, but rather to deepen our appreciation and inspire a sense of responsibility. Current understanding suggests that preserving this extraordinary biodiversity is not just about protecting individual species. It is about maintaining the health and resilience of the entire planet. The ocean's ecosystems provide invaluable services to humanity, from regulating climate and producing oxygen to supplying food and supporting livelihoods. As we conclude this chapter on the boundless life within the ocean, we encourage you to carry this sense of awe and connection. The ocean is not merely a collection of facts, it is a living, breathing entity, a vibrant, complex world teeming with mysteries yet to be unravelled. With every fact we uncover, we gain a small window into the vast and interconnected tapestry of marine life, inviting us to contemplate its beauty, respect its power, and understand our vital role as stewards of this magnificent blue planet. Let your mind gently absorb these truths, allowing the wonder of the ocean's life to wash over you, bringing a profound sense of peace and interconnectedness. We have journeyed through the ocean's profound depths, its dynamic processes, and the vibrant tapestry of life it sustains. We have also acknowledged the pressing challenges it faces, the echoes of human impact rippling through its delicate balance. Yet, as we gently turn our focus, we discover that the ocean is not merely a recipient of our actions, it is an active, vital force, intricately woven into the very fabric of our planet's existence, shaping our weather, fueling our economies, and holding untold potential for our future. Imagine, if you will, the vast shimmering surface of the ocean, stretching beyond the horizon. We often perceive it as a separate entity, but in truth, it is the beating heart of Earth's climate system, a colossal engine driving the very air we breathe and the weather we experience daily. Research shows that the ocean's capacity to absorb, store, and redistribute heat is unparalleled. It acts as a massive thermal battery, moderating global temperatures and preventing far more extreme climatic shifts. This immense thermal inertia means that even small changes in ocean temperature can have profound, far-reaching consequences across the globe. Consider the powerful cyclical phenomena like the El Niño Southern Oscillation, ENSO. Scientists have observed that this recurring climate pattern, originating in the tropical Pacific Ocean, dramatically influences weather conditions worldwide. During an El Niño event, warmer than average sea surface temperatures in the eastern Pacific shift rainfall patterns, leading to droughts in some regions and heavy floods in others. Conversely, La Niña brings cooler waters and often opposite effects. These oceanic pulsations demonstrate the profound interconnectedness of the marine realm with atmospheric circulation, illustrating how the ocean's gentle currents can orchestrate powerful shifts in global weather, from altering monsoon seasons to influencing hurricane intensity. We also see the ocean's direct influence in the genesis and power of tropical storms. Hurricanes, typhoons, and cyclones are born over warm ocean waters, drawing immense energy from the heat and moisture rising from the surface. The warmer the ocean, the more fuel these formidable storms accumulate, leading to increased intensity and destructive potential. Studies indicate that as ocean temperatures continue to rise, the frequency of the most powerful storms may increase, posing greater threats to coastal communities and ecosystems. The ocean, in its immense power, reminds us of the delicate balance between its life-giving warmth and its capacity for formidable expression. Beyond these dramatic events, the ocean is a quiet, continuous driver of the global water cycle. We breathe in the air, and a significant portion of the moisture within it has evaporated from the ocean's surface. This process, driven by solar energy, lifts billions of tons of water vapor into the atmosphere each day, forming clouds that eventually release their precious cargo as rain or snow over land and sea. In this elegant, ceaseless dance, the ocean provides the fresh water essential for life on Earth, a subtle yet profound testament to its fundamental role in sustaining us all. It is a constant, gentle reminder that every drop of rain carries a whisper of the ocean within it. As we contemplate the ocean's climatic influence, we also recognize its deep entanglement with human civilization and our global economy. For centuries, the ocean has served as a grand highway, facilitating trade and connecting cultures across continents. Today, over 90% of global trade is transported by sea, carried by vast container ships that ply its endless routes. This intricate network of shipping lanes is the lifeblood of international commerce, a testament to the ocean's enduring role in shaping our modern world. Imagine the silent, tireless journey of these vessels, bridging immense distances, carrying goods that touch every aspect of our daily lives. The ocean also provides us with a significant portion of our food. Fisheries, both large-scale industrial operations and small artisanal endeavours, supply protein to billions of people worldwide. While we acknowledged the perils of overfishing in our previous exploration, it is also important to recognise the ocean's immense potential as a sustainable food source when managed responsibly. Aquaculture, the farming of marine organisms, is a rapidly growing industry, offering a way to meet increasing demand while potentially reducing pressure on wild fish stocks. Current understanding suggests that innovative, environmentally sound aquaculture practices will be crucial for food security in the coming decades, allowing us to harvest the ocean's bounty without depleting its future. Beyond food and transport, the ocean holds vast energy resources. For decades, we have extracted oil and natural gas from beneath its seabed, fueling our industries and homes. However, as we look towards a more sustainable future, the ocean offers promising avenues for renewable energy. Offshore wind farms are harnessing the steady power of marine winds, while emerging technologies are exploring the potential of wave and tidal energy, converting the ocean's ceaseless motion into clean electricity. These innovations represent a profound shift, transforming our relationship with the ocean from one of extraction to one of harmonious collaboration, tapping into its natural rhythms for a cleaner tomorrow. The ocean's economic impact extends to the vibrant realm of tourism and recreation. Coastal communities thrive on the allure of pristine beaches, the thrill of surfing, the tranquility of sailing, and the wonder of underwater exploration through diving and snorkeling. Marine ecotourism, such as whale watching and guided reef tours, not only provides livelihoods but also fosters a deeper appreciation and understanding of marine ecosystems, creating ambassadors for conservation. We find joy, solace, and inspiration in its boundless expanse, and this connection translates into significant economic value, reminding us of the ocean's multifaceted gifts. Perhaps one of the most exciting, yet still largely untapped economic frontiers lies in marine bioprospecting. The incredible biodiversity of the ocean, especially in its extreme environments, is a treasure trove of unique chemical compounds and genetic material. Scientists are actively exploring marine organisms for potential new medicines, industrial enzymes, and biotechnological applications. Imagine a future where a cure for a disease or a revolutionary new material is discovered in the depths of a coral reef or within a deep-sea vent organism. The ocean, in its silent, intricate wisdom, holds the blueprints for countless solutions we have yet to uncover, offering a glimpse into a future shaped by its hidden potential. Given the ocean's indispensable roles as a climate regulator, an economic engine, and a source of profound wonder, our responsibility to protect it becomes undeniably clear. We are not just preserving nature, we are safeguarding our own future. This understanding has led to a global movement towards more proactive and effective conservation strategies. One of the most vital tools in ocean conservation is the establishment of marine protected areas, MPAs. These designated zones, similar to national parks on land, restrict or prohibit certain human activities to allow marine ecosystems to recover and thrive. Research shows that well-managed MPAs can lead to increased biodiversity, larger fish populations, and greater resilience to environmental stresses, acting as vital nurseries that replenish surrounding areas. Imagine these underwater sanctuaries as peaceful havens, allowing life to flourish without constant pressure, slowly restoring the intricate balance of the marine world. Beyond protected areas, sustainable practices are gaining momentum across various sectors. In fishing, this means implementing quotas, regulating fishing gear to reduce bycatch, unwanted species caught accidentally, and supporting certified sustainable fisheries. For aquaculture, it involves developing methods that minimize environmental impact, such as using sustainable feed and preventing the escape of farmed species. In our daily lives, reducing our consumption of single-use plastics and supporting policies that promote circular economies are crucial steps in combating the pervasive issue of plastic pollution. Every conscious choice, every small action, contributes to the larger wave of change. Current understanding suggests that technological innovation will play a pivotal role in our stewardship of the ocean. Advanced monitoring systems using satellites, underwater drones, and AI are helping us better understand ocean health, track marine life, and detect illegal fishing. Breakthroughs in materials science are leading to biodegradable alternatives to plastic, while engineering solutions are being developed to clean up existing plastic pollution. These tools, wielded with wisdom and care, empower us to be more effective guardians of the blue realm. Ultimately, the future of the ocean, and thus our own, hinges on global cooperation and a shared sense of responsibility. International agreements, collaborative research initiatives, and public awareness campaigns are essential to address challenges that transcend national borders, such as climate change, ocean acidification, and transboundary pollution. We are all connected to the ocean, no matter how far inland we may live, and our collective actions will determine its fate. As we gently bring this chapter to a close, we are left with a profound sense of awe and a renewed commitment. The ocean, in its vastness and complexity, continues to hold secrets yet to be unveiled, wonders yet to be fully appreciated. It is a living, breathing entity, resilient yet vulnerable, offering us both endless bounty and urgent warnings. Our journey through these facts is not just an intellectual exercise, it is an invitation to deepen our connection, to listen to the ocean's intricate patterns, and to act with the subtle wisdom it imparts. May our understanding inspire a peaceful resolve to protect this magnificent blue heart of our planet, ensuring its enduring embrace for generations to come. As we gently drift through the vast expanse of our oceanic knowledge, having touched upon its staggering scale, its intricate chemistry, its vibrant tapestry of life, and its profound influence on our planet's very breath and pulse, we arrive at a compelling truth. For all we have discovered, For every fact we have unearthed, the ocean remains an enigma of breathtaking proportions. It is a realm of enduring mystery, a silent testament to the boundless wonders that still lie beyond our current understanding. Imagine settling into a quiet space, allowing your mind to expand, to truly grasp the immensity of what remains unseen. We have only just begun to scratch the surface of this watery world, a mere fraction of its depths and its secrets revealed. Research suggests that over 80% of the ocean, particularly its deep-sea environments, remains entirely unexplored by human eyes or instruments. Think of that. Vast, shimmering depths, stretching for miles beneath us, where life forms exist in conditions so extreme they defy our terrestrial imagination, and where geological processes unfold on timescales that dwarf human history, all waiting to be encountered. It is within these unexplored reaches that the ocean continues to guard its most profound secrets. Consider the mesopelagic zone, often referred to as the Aeseus, quote, 7, lying between 660 and 3,300 feet, 201 meters below the surface. Here, the last faint whispers of sunlight fade into perpetual gloom, yet it is far from devoid of life. Studies indicate that this zone might harbour the largest biomass of vertebrates on Earth, primarily small, bioluminescent fish and crustaceans that undertake one of the planet's largest daily migrations, ascending to the surface at night to feed and retreating into the depths by day. We are only just beginning to comprehend the ecological significance of this immense bustling layer, a critical link in the global carbon cycle, largely unseen and unquantified. The sheer volume of life here, performing its silent rhythmic dance, reminds us of the ocean's capacity to surprise, to defy our assumptions about where and how life can thrive. Deeper still, beyond the twilight zone lies the abyssal plain, a vast, cold, dark expanse covering more than half of Earth's surface. Here, crushing pressures, near freezing temperatures, and a scarcity of food create an environment that would seem utterly inhospitable. Yet, life persists, often in forms so unique and specialized they appear alien. We encounter creatures with highly adapted sensory organs, some relying on chemosynthesis where sunlight never penetrates, others existing as mere shadows, patiently waiting for the sparse bounty of marine snow to drift down from above. Each discovery in these realms, a new species of deep-sea octopus, a previously unknown hydrothermal vent community, or a unique microbial ecosystem thriving within the seafloor, is not just a scientific finding, it is a profound expansion of our understanding of life's resilience and adaptability. Scientists estimate that millions of species in the ocean, from microorganisms to larger invertebrates and fish, are yet to be formally described, their intricate roles in the global ecosystem still unknown. This vast, undiscovered biodiversity represents a treasure trove of potential scientific breakthroughs, from novel biochemical compounds to insights into evolutionary processes. To peer into these hidden worlds, we rely on an ever-evolving suite of technological marvels, pushing the boundaries of engineering and human ingenuity. Remotely operated vehicles, ROVs, tethered to research vessels by long cables, allow us to send sophisticated cameras, manipulators, and sensors into extreme depths, relaying real-time images and data back to the surface. These robotic explorers become our eyes and hands in environments where humans cannot safely venture, meticulously collecting samples, mapping the sea floor, and observing delicate ecosystems without disturbance. Autonomous underwater vehicles, AUVs, on the other hand, operate independently, pre-programmed to follow specific paths, gather vast amounts of data over extended periods, and map vast swathes of the seafloor with unprecedented detail. They are silent, tireless cartographers, slowly rendering the previously blank pages of our oceanographic maps into rich, topographical tapestries. Manned submersibles, too, continue to play a vital role, offering a direct, albeit brief, human presence in the deep. Vessels like the iconic Alvin, or more modern submersibles capable of reaching the deepest points in the ocean, provide scientists with a unique perspective, a visceral connection to these remote environments that no robotic eye can fully replicate. Imagine the sensation of gazing out of a small viewport, miles beneath the surface, witnessing a landscape sculpted by unimaginable pressures and time, illuminated only by the submersible's powerful lights. It is an experience that humbles and inspires, reinforcing our commitment to understanding this alien world. Beyond direct exploration, our understanding is also being revolutionized by advancements in satellite oceanography. From orbit, constellations of satellites continuously monitor vast oceanic parameters: sea surface temperature, ocean color, indicating phytoplankton blooms, sea level rise, and even the subtle gravitational anomalies that reveal the topography of the seafloor hidden beneath miles of water. These global vantage points provide an unparalleled macro perspective, allowing us to track large-scale phenomena, understand ocean currents, and monitor the health of marine ecosystems across entire ocean basins. Even the very building blocks of life are yielding new insights. Environmental DNA, or eDNA, is emerging as a powerful, non-invasive tool. By simply collecting a water sample, scientists can detect trace amounts of DNA shed by marine organisms, from fish scales and mucus to microbial cells, allowing them to identify species present in an area without ever seeing or capturing them. This technique offers a revolutionary way to survey biodiversity, track elusive or rare species, and monitor the health of ecosystems, opening up possibilities for understanding marine life on scales previously unimaginable. It is like listening to the genetic whispers of an entire ecosystem, revealing its hidden inhabitants. As we look forward to these frontiers of discovery, it is also essential to reflect on the ocean's ancient past, for its history is inextricably linked to our planet's very existence. The ocean itself is billions of years old, its waters having been present on Earth for an astonishing span of geological time, shaping continents, regulating climate, and serving as the cradle of life itself. Studies of ancient ocean sediments and fossil records tell us that the first life forms emerged in the primeval seas, simple single-celled organisms that slowly, over eons, evolved into the incredible diversity we see today. The ocean, then, is not just a habitat. It is a living archive of Earth's evolutionary journey. We continue to uncover evidence of the dynamic processes that have shaped the ocean floor over hundreds of millions of years. Plate tectonics, the slow but relentless movement of Earth's crustal plates, is nowhere more evident than in the ocean basins. Mid-ocean ridges, vast underwater mountain ranges stretching for tens of thousands of miles, are where new oceanic crust is continuously formed as magma rises from the Earth's mantle. This process, known as seafloor spreading, gradually pushes continents apart, creating and reshaping ocean basins over geological timescales. Conversely, at deep ocean trenches, such as the Mariana Trench, older oceanic crust is subducted or pulled back down into the Earth's mantle, a process that recycles material and drives volcanic activity and earthquakes along continental margins. The ocean floor, far from being a static, featureless plane, is a dynamic, ever-changing landscape, a testament to the planet's internal forces. Paleoceanography, the study of the ocean's past, allows us to decipher these ancient stories. By analysing sediment cores extracted from the seafloor, which act like geological time capsules, scientists can reconstruct past ocean temperatures, salinity levels, current patterns, and even the composition of ancient atmospheres. These insights are invaluable, providing critical context for understanding present-day climate change and predicting future oceanic responses. They remind us that the ocean has experienced dramatic shifts throughout its history, but the current rate of change driven by human activity is unprecedented. Thus, the journey of understanding the ocean is an enduring quest, a continuous unfolding of wonder and knowledge. The 100 facts about the ocean we have explored together are but small windows into the vast and interconnected tapestry of this global system. Each fact, each discovery, illuminates a piece of the puzzle, deepening our appreciation for its complexity and profound significance. The ocean is a constant teacher, a source of endless fascination, reminding us of the limits of our current understanding and the boundless potential for future revelations. As we bring this particular guided exploration to a close, we invite you to carry this sense of wonder and curiosity with you. The ocean, in its immense and silent power, continues its work, regulating our climate, supporting an extraordinary web of life, and holding untold mysteries within its depths. Our role, as observers and inhabitants of this blue planet, is to remain open to its lessons, to protect its delicate balance, and to continue the gentle current of knowledge, always seeking to understand more, always striving to act with wisdom and reverence. For in the ocean's health lies the very pulse of our world, and in its enduring mystery a timeless invitation to explore, to learn, and to simply be in awe. As we gently drift through the quiet currents of our shared contemplation, we find ourselves at the edge of an even grander mystery, the vast, uncharted territories of the ocean that remain an enigma of breathtaking proportions. We have touched upon its immense scale, its profound influence, and the vibrant life it harbours, yet, as scientists often remind us, over 80% of this watery realm remains unexplored. This is not merely a statistic, it is an invitation to consider the boundless wonders that lie hidden, waiting to be perceived, understood, and cherished. Imagine, if you will, the sheer volume of water, the crushing weight of it, the absolute darkness that reigns supreme in depths where sunlight has never dared to penetrate. This is the ultimate frontier on our own planet, a world more alien than the surface of Mars, teeming with life forms and geological features we are only just beginning to conceptualize. The challenges of exploring these abyssal plains, the vast mid-ocean ridges, and the deepest trenches are immense, demanding ingenuity, perseverance, and a profound respect for the extreme conditions. To unveil these secrets, we have developed remarkable technologies, extending our senses into environments where human physiology cannot directly venture. Remotely operated vehicles, or ROVs, serve as our eyes and hands in the deep. These tethered robots, controlled from research vessels far above, can withstand pressures that would instantly crush a human. They carry high-definition cameras, powerful lights, and sophisticated sampling equipment, allowing us to capture stunning images of previously unseen creatures, collect geological samples from hydrothermal vents, and even deploy instruments for long-term monitoring. Research shows that ROVs have been instrumental in discovering new species at an astonishing rate, revealing ecosystems that thrive independently of the sun's energy. Complementing ROVs are autonomous underwater vehicles, or AUVs. These untethered robots are programmed to follow specific paths, collecting data on ocean currents, salinity, temperature, and seafloor topography without direct human control. They can cover vast distances, mapping expansive areas of the ocean floor with unprecedented detail. Piecing together the intricate puzzle of submerged mountain ranges, canyons, and volcanic landscapes, scientists have observed that AUVs are particularly effective for wide-area surveys, providing the foundational maps that guide more focused ROV explorations. Yet, there is a unique allure to human presence in the deep, a testament to our innate drive for direct experience. Manned submersibles, such as the legendary Alvin or the more recent limiting Factor, carry small crews to the deepest parts of the ocean, offering a first-hand, albeit brief, encounter with these extreme environments. From the porthole of a submersible, bathed in the glow of powerful external lights, you can witness the bioluminescent ballet of deep-sea creatures, the slow-motion dance of hydrothermal vent chimneys, and the stark beauty of ancient geological formations. Studies indicate that the human eye and mind, with their capacity for pattern recognition and intuitive leaps, often notice details that automated systems might miss, sparking new hypotheses and accelerating discovery. Beyond direct observation, we employ sound to paint a picture of the ocean's hidden landscapes. Sonar technology, which uses sound waves to detect objects and map topography, is our primary tool for visualizing the seafloor. By emitting sound pulses and measuring the time it takes for the echoes to return, we can create detailed bathymetric maps, revealing the majestic scale of underwater mountain ranges, vast abyssal plains, and the dramatic drop-offs of ocean trenches. Current understanding suggests that less than 25% of the global seafloor has been mapped with modern, high-resolution sonar, leaving immense stretches of our planet's largest habitat largely unknown to us. From the surface of our planet, satellites offer another perspective, peering into the ocean's dynamic skin. Satellite oceanography allows us to monitor sea surface temperature, track the movement of major ocean currents, measure sea level rise, and even detect the subtle hues of phytoplankton blooms across vast expanses. These eyes in the sky provide a macroscopic view, revealing the interconnectedness of ocean systems on a global scale and helping us understand phenomena like El Niño and La Niña, which profoundly impact global weather patterns. As we delve into these depths, whether through advanced technology or the occasional human expedition, we begin to perceive the ocean not just as a physical space, but as a symphony of sensory experiences far beyond our own. We have briefly mentioned bioluminescence, but its prevalence and diversity in the deep sea are truly astounding. In the perpetual night of the aphotic zone, light is not a gift from the sun but a self-generated marvel. Research shows that countless organisms, from tiny dinoflagellates to colossal squid, produce their own light through complex chemical reactions. This living light serves myriad purposes, attracting mates, luring prey, startling predators, or camouflaging against the faint glow of other bioluminescent creatures. Imagine a world where every flash, every spark, is a form of communication, a silent language spoken in bursts of ephemeral light. The ocean also possesses a profound soundscape, a world of acoustic wonders that often goes unheard by human ears. Natural sounds abound. The mournful songs of whales travelling vast distances, the clicks and whistles of dolphins navigating their intricate social lives, the crackling chorus of snapping shrimp, the thunderous rumble of underwater volcanoes erupting, and the subtle groans of shifting tectonic plates. Studies indicate that many marine species rely heavily on sound for navigation, hunting, communication, and reproduction. For them, the ocean is a vibrant auditory environment, a constant flow of information. However, this natural symphony is increasingly being overwhelmed by anthropogenic, or human-generated, noise, the incessant hum of cargo ships, the explosive blasts of seismic air guns used for oil and gas exploration, the piercing pings of military sonar, and the clamour of construction projects all contribute to a cacophony that can disorient, stress, and even harm marine life. Scientists have observed that this noise pollution interferes with essential behaviours, forcing animals to shout over the din or abandon critical habitats, disrupting the delicate balance of their underwater world. Furthermore, in the absence of light, many deep-sea creatures rely on an exquisite sense of chemoreception, essentially a highly refined sense of smell and taste. They detect subtle chemical cues in the water, navigating by gradients of dissolved compounds, locating food sources, identifying mates, and sensing the presence of predators or rivals. Imagine a world where information is carried not by light or sound, but by an invisible tapestry of chemical signals, each thread telling a story of life and survival in the dark. This glimpse into the sensory worlds of marine life only deepens our appreciation for the sheer scale of undiscovered life. We speak of millions of marine species yet to be formally described, their intricate ecological roles largely unknown. Every expedition into a new deep-sea environment, every exploration of a previously unvisited seamount, brings forth a cornucopia of new organisms, new fish, new crustaceans, new corals, new microbes. Research shows that entire phyla, major classifications of life, may still await discovery in the ocean's depths, challenging our understanding of evolution and biodiversity. Each new discovery is a small window into the vast and interconnected tapestry of life, reminding us of the immense biological richness that lies beneath the waves. The potential held within these undiscovered species and ecosystems is staggering. Marine bioprospecting, the search for novel compounds from marine organisms, has already yielded breakthroughs in medicine, biotechnology, and industrial applications. From sponges providing anti-cancer agents to deep-sea microbes offering enzymes that thrive in extreme conditions, the ocean is a vast, untapped pharmacy and laboratory. Current understanding suggests that the vast majority of marine genetic and biochemical diversity remains unexplored, holding promises for new antibiotics to combat drug-resistant infections, new enzymes for industrial processes, and novel materials for technological advancements. However, this potential also comes with ethical considerations, demanding careful stewardship to ensure that the benefits are shared equitably and that bioprospecting is conducted sustainably, without harming the delicate ecosystems from which these treasures emerge. As we conclude this chapter on the ocean's profound mysteries, we are left with a sense of humility and awe. The ocean is not merely a collection of facts, but a living, breathing entity, constantly evolving, perpetually surprising. Its vast unknowns remind us that our journey of discovery is far from over, that there are countless secrets still awaiting our gentle inquiry. This deep, quiet contemplation of what we do not yet know about the ocean fosters a profound sense of wonder, encouraging us to remain open, curious, and ever respectful of the immense power and beauty of our blue planet. It is a call to protect what we know, to explore what we don't, and to cherish the very act of discovery itself, allowing the gentle current of knowledge to carry us further into the ocean's embrace. As we gently drift further into the vastness of oceanic knowledge, a new horizon beckons, not of what we understand, but of the profound mysteries that still shroud the deep. We have journeyed through the known, but now let us turn our gaze to the uncharted, to the silent, shimmering realms that remain largely hidden, and to the urgent whispers of the challenges that threaten these precious secrets. Settle in, breathe deeply, and allow your mind to expand with the sheer wonder of the unknown. Research shows that over 80% of the ocean remains unexplored. Imagine, for a moment, an entire world, more than 3/4 of its vast expanse still holding its breath, its landscapes and inhabitants unseen by human eyes. It is a staggering thought, a testament to the ocean's immense scale and the formidable challenges of venturing into its depths. We speak of space exploration with awe, yet a world of equal, if not greater, mystery lies beneath the waves, right here on our own planet. This unexplored majority includes not only the abyssal plains, but also vast stretches of the mesopelagic zone, often called the twilight zone, where sunlight barely penetrates, casting an ethereal glow upon an unknown diversity of life. Here, creatures adapt to perpetual dimness, their forms and behaviors evolving in ways we are only beginning to comprehend, creating a living tapestry woven with intricate patterns, subtle wisdom, and unimaginable adaptations. Scientists have observed that millions of marine species are yet to be discovered and described. Even as our understanding of marine biodiversity grows, the sheer volume of life waiting to be catalogued is immense. We are continually finding new species, from microscopic organisms that form the very base of the food web, to larger, more complex beings hidden in the deepest trenches or within the crevices of hydrothermal vents. It is not merely a matter of finding new variations of known species. Current understanding suggests that entire phyla, fundamental branches of the tree of life, could still be awaiting discovery in the ocean's most remote corners. Each new discovery offers a fresh perspective on evolution, adaptation, and the incredible resilience of life, reminding us that the ocean is a boundless repository of biological innovation, a living library whose vast majority of volumes remain unread. Studies indicate that less than 25% of the global seafloor has been mapped with high-resolution sonar. Think of our terrestrial continents, their mountains, valleys, and plains meticulously charted. Now, envision the ocean floor, a landscape even more varied and dramatic, yet mostly obscured. We know more about the surface of Mars than we do about the detailed topography of our own planet's seabed. This lack of comprehensive mapping means that vast underwater mountain ranges, deep canyons, expansive plains, and intricate geological formations exist beyond our current knowledge. Each unmapped area could harbour unique ecosystems, undiscovered mineral resources, or provide crucial clues about Earth's geological history and plate tectonics. The seafloor is not a uniform basin. It is a dynamic, ever-changing world of its own, sculpted by immense forces, and its secrets are patiently awaiting the sonar's beam. The full ecological significance of vast areas, particularly the mesopelagic zone, is largely unquantified. We understand the vital roles of surface waters and the vibrant ecosystems of coral reefs and kelp forests. But what about the deep, dark layers? The mesopelagic zone, extending from about 200 to 1,000 meters deep, is home to an immense biomass of fish, squid, and crustaceans that undertake daily vertical migrations, ascending to feed at night and descending by day. This diel vertical migration is the largest animal migration on Earth, yet its precise impact on carbon cycling, nutrient distribution, and the global food web is still a subject of intense research. These twilight dwellers play an essential yet poorly understood role in sequestering carbon from the atmosphere and distributing nutrients throughout the water column, making them critical players in the planet's overall health. Moreover, the potential within marine bioprospecting remains largely untapped. The ocean's extreme environments have driven the evolution of organisms with unique biochemical pathways and molecular structures. These adaptations hold immense promise for human benefit, from new pharmaceuticals to industrial enzymes and biotechnological innovations. We have already discovered anti-cancer agents derived from marine sponges, pain relievers from cone snails, and potent antibiotics from deep-sea bacteria. Yet these discoveries represent only a tiny fraction of what lies beneath. Each newly discovered species, each adaptation to high pressure, extreme temperature, or lack of light could hold the key to breakthroughs in medicine, sustainable energy, or material science. The ocean is a living pharmacy, a vast natural laboratory, and we have barely begun to read its labels. As we contemplate these profound unknowns, a shadow begins to fall across the serene waters of discovery. The very health of the ocean, the custodian of these secrets, is increasingly threatened by human activity. The challenges facing our marine world are complex and interconnected, demanding our immediate attention and collective action. Let us turn our awareness now to these pressing concerns, not with fear, but with a calm resolve to understand and protect. One of the most insidious threats is ocean acidification. As we release ever-increasing amounts of carbon dioxide into the atmosphere, a significant portion of it is absorbed by the ocean. While this buffering action helps mitigate climate change, it comes at a cost. the CO2 reacts with seawater to form carbonic acid, leading to a decrease in the ocean's pH. This seemingly small chemical change has profound implications. It makes it harder for marine organisms, particularly those with calcium carbonate shells or skeletons, like corals, oysters, clams, and microscopic pteropods, to build and maintain their protective structures. Imagine a world where the very building blocks of life are dissolving, where the foundations of entire ecosystems are weakening. The delicate balance of these organisms is vital, as they form the base of many marine food webs and provide critical habitat for countless other species. Closely linked to acidification, and perhaps more visibly devastating, is coral bleaching. Rising ocean temperatures, primarily due to climate change, stress corals, causing them to expel the symbiotic algae, zooxanthellae, that live within their tissues and provide them with essential nutrients and their vibrant colours. Without these algae, corals turn white, appearing, quote, 12. While corals can sometimes recover from mild bleaching events, severe or prolonged stress often leads to widespread coral mortality. We have witnessed unprecedented mass bleaching events across the globe, transforming once vibrant, teeming coral reefs, the rainforests of the sea, into ghostly graveyards. The loss of these intricate ecosystems has ripple effects throughout the marine environment, impacting fish populations, coastal protection, and the livelihoods of millions. Overfishing also continues to deplete marine populations at an alarming rate. Our demand for seafood has outpaced the ocean's ability to replenish itself, leading to the collapse of many commercially important fish stocks. Beyond the targeted species, unsustainable fishing practices often result in significant bycatch, the accidental capture of non-target species, including marine mammals, sea turtles and seabirds, which are then discarded, often dead or dying. Destructive fishing methods such as bottom trawling physically damage seafloor habitats, tearing up coral gardens and disturbing vital nursery grounds. The intricate balance of marine ecosystems is disrupted, threatening biodiversity and undermining the long-term sustainability of our ocean's resources. Then there is the pervasive issue of plastic pollution. From the smallest microplastics, invisible to the naked eye, to vast accumulations of debris forming. Quote 14. In ocean gyres, plastic has infiltrated every corner of the marine environment. Marine animals, from tiny zooplankton to majestic whales, mistake plastic fragments for food, leading to internal injuries, starvation, and toxic contamination. Larger plastic items entangle marine life, causing injury, suffocation, and drowning. This persistent, non-biodegradable material breaks down into smaller and smaller pieces, entering the food chain and eventually making its way back to us. The scale of this problem is immense, a stark reminder of our global footprint. Habitat destruction extends beyond the impacts of fishing gear. Coastal development, dredging for ports, and pollution from land-based sources directly destroy critical marine habitats like mangrove forests, seagrass beds, and estuaries. These areas are vital nursery grounds for many fish species, carbon sinks, and natural buffers against coastal erosion and storm surges. Their degradation represents a significant loss of biodiversity and ecosystem services, further weakening the ocean's resilience. Finally, a less visible but increasingly recognized threat is anthropogenic noise pollution, The constant din from shipping traffic, seismic surveys for oil and gas exploration, military sonar and offshore construction projects permeates the ocean, disrupting the delicate acoustic environment that many marine species rely upon. Whales and dolphins, for instance, use sound for communication, navigation, foraging, and mating. Excessive noise can mask these vital signals, causing stress, disorientation, and even physical harm. It can drive marine mammals away from critical feeding or breeding grounds, interfere with their ability to find mates, and lead to strandings. The ocean, once a realm of natural sounds, is becoming increasingly noisy, altering the very fabric of marine life. As we absorb these challenging realities, we recognize that the health of the ocean is inextricably linked to the health of our planet and our own well-being. The vast, unexplored wonders and the delicate balance of life within its depths are under pressure. But understanding these challenges is the first step towards finding solutions, towards nurturing the profound respect and awe that the ocean so deeply deserves. Let us hold these truths gently, allowing them to foster not despair, but a renewed sense of purpose and a calm commitment to stewardship. As we drift deeper into this tranquil space, we realize that for all the facts we've gathered, for all the wonders we have touched upon, the ocean still guards more secrets than it has revealed. Its vastness is not just spatial, encompassing unimaginable depths and expansive surfaces. It is also biological, a testament to life's boundless creativity and resilience, a world teeming with untold stories yet to be discovered. Imagine, if you will, the sheer volume of life yet to be catalogued, organisms existing in realms we are only just beginning to glimpse. Each new discovery is not merely a name added to a list. It is a key, unlocking deeper understanding of evolution, adaptation, and the delicate balance of Earth's ecosystems. Scientists are continually uncovering new species of deep-sea microbes, for instance, some thriving in conditions previously thought impossible for life: intense heat, crushing pressure, or complete absence of light. These extremophils offer profound insights into the origins of life itself, or even the potential for life beyond Earth. Others, like the remarkable bone-eating worms of the Osedax genus, reveal novel and ingenious ways life recycles nutrients in the most barren environments, transforming the remains of whales into vibrant localized ecosystems. This ongoing parade of discovery highlights the urgent need for continued exploration. We are racing against time, for even as we celebrate these wondrous new findings, we are acutely aware of their fragility. Many of these newly found species, and countless others still unknown, reside in environments increasingly vulnerable to human impact. The slow, relentless creep of ocean acidification, the distant rumble of seismic exploration, the invisible spread of microplastics, all pose existential threats to life we haven't even had the chance to name, to understand, or to appreciate. The ocean's vast biodiversity is a library, and we are losing books before we even know they exist. Yet, our understanding of the ocean extends beyond cataloguing its inhabitants. We turn our gaze now to another profound, yet often unseen, service the ocean provides, its capacity as a subquote 15 sink. This refers to the carbon captured by the world's ocean and coastal ecosystems, mangroves, tidal marshes, and seagrass beds, which are incredibly efficient at sequestering carbon from the atmosphere and storing it in their biomass and sediments. We have touched upon the ocean's role in absorbing carbon dioxide, but these specific coastal habitats offer a concentrated, powerful solution. Research consistently shows that these vibrant coastal ecosystems can store up to 5 times more carbon per hectare than terrestrial forests, and they do so for millennia, often locking away carbon in their waterlogged soils where decomposition is slow. Seagrass meadows, for example, cover less than 0.2% of the world's oceans but are responsible for more than 10% of the carbon buried in ocean sediments annually. Mangrove forests, with their intricate root systems, not only sequester massive amounts of carbon, but also protect coastlines from storm surges and provide critical nurseries for countless marine species. Tidal marshes, often found in temperate zones, also play a significant role, accumulating deep layers of carbon-rich sediment over centuries. Protecting and restoring these natural carbon sinks is not just about safeguarding biodiversity. It is a powerful, nature-based solution to climate change, a silent ally in our quest for a healthier planet. Every acre of mangrove forest saved, every hectare of seagrass restored, contributes directly to mitigating global warming, providing a breath of fresh air for both the planet and its inhabitants. These ecosystems are living testament to the ocean's deep wisdom and its inherent ability to regulate Earth's climate, if only we allow it to function. This knowledge, this deeper appreciation of the ocean's intricate workings, inspires us to act. It fuels the tireless efforts of scientists, conservationists, and communities around the globe who are working to understand and protect these precious realms. Consider the growing network of marine protected areas, or MPAs. These are designated zones where human activities are restricted to varying degrees, allowing marine ecosystems to recover and thrive. They serve as vital refuges for endangered species, nurseries for fish populations, and living laboratories for scientific research, offering a glimpse into what healthy, undisturbed ocean ecosystems truly look like. Studies consistently demonstrate that well-managed MPAs lead to increased biodiversity, larger fish sizes, and greater ecosystem resilience, with benefits often spilling over into adjacent fishing grounds. They are tangible expressions of our commitment to stewardship, providing hope and a path forward for the ocean's recovery. From vast stretches of the open ocean to critical coastal habitats, MPAs are being established and expanded, creating sanctuaries where life can flourish away from the most intense human pressures. They are not merely fences in the water, they are investments in the future, allowing the ocean's natural processes to heal and replenish. Yet, the health of the ocean is not solely dependent on grand scientific expeditions or vast protected zones. It is also shaped by our daily choices, by the ripple effect of individual actions. As we absorb these facts, we invite you to reflect on your own connection to this magnificent blue world. Perhaps it is a memory of a tranquil beach, the rhythmic sound of waves, or simply the knowledge that the air you breathe and the climate that sustains us are intimately linked to the ocean's health. Every choice we make, however small, from reducing our plastic consumption to supporting sustainable seafood, from advocating for stronger environmental policies to simply sharing our wonder with others, ripples through this interconnected system, contributing to its well-being. The ocean has a profound memory too. Within its sediments, locked in ancient ice cores from polar regions, and etched into the growth rings of corals, lies a historical record of Earth's climate and environmental changes spanning millennia. Scientists study these natural archives to understand past climate patterns, ocean temperatures, and atmospheric compositions, which in turn helps us predict future scenarios and contextualize the rapid changes we observe today. This oceanic memory provides critical data, reminding us that while the ocean is vast, it is not limitless in its capacity to absorb our impacts without consequence. It tells a story of cycles and shifts, of resilience and vulnerability, urging us to listen to its ancient wisdom. Long-term ocean observatories, equipped with an array of sensors and autonomous vehicles, are now continuously monitoring key oceanographic parameters: temperature, salinity, currents, pH, oxygen levels, and even marine soundscapes across vast regions. These observatories provide invaluable real-time data, allowing scientists to track changes over time, identify emerging threats, and understand the complex dynamics of ocean processes on a global scale. They are the eyes and ears of our collective scientific endeavour, patiently gathering information that is crucial for informed decision-making and effective conservation strategies. As we conclude this chapter of our journey, let the ocean continue to be your guide, a source of endless wonder and profound wisdom. Its depths remind us of the mysteries yet to unfold, its currents of the constant flow of life, and its vastness of our shared responsibility. We are all part of this grand blue tapestry, and in understanding it, we find a deeper understanding of ourselves and our place within the natural world. May this peaceful immersion leave you with a renewed sense of calm and an enduring curiosity for the magnificent ocean that cradles our planet. As we continue our quiet journey, gently drifting through the vast, shimmering depths of oceanic knowledge, we find ourselves contemplating not just the ocean's profound memory and its vital role as a blue carbon sink, but also the intricate ways we strive to listen to its whispers, to decipher its complex language. Our understanding of this liquid heart of our planet is an ever-evolving tapestry, woven with threads of tireless research, cutting-edge technology, and an unyielding sense of wonder. You see, for all the ocean's ancient wisdom and its seemingly boundless expanse, our ability to truly comprehend its intricate systems has only truly blossomed in recent decades. We are no longer content to merely skim its surface or plumb its depths with simple lines. Instead, we have begun to build a global network of senses, an extended consciousness that allows us to monitor its pulse, measure its breath, and track its every subtle shift. The Global Ocean Observing System, GOES, is a vast international network of instruments that continuously monitors the ocean's health and dynamics. Imagine, if you will, a silent, sprawling orchestra of robotic explorers scattered across every ocean basin, each playing a crucial note in the symphony of data that helps us understand our world. This isn't science fiction. It is the reality of GOES. Thousands of robotic floats known as Argo floats drift through the water column, regularly diving to depths of 2,000 meters and then resurfacing, transmitting critical data on temperature, salinity, and currents back to satellites. These unassuming devices are like a fleet of silent sentinels, providing an unprecedented three-dimensional view of the upper ocean's physical state, filling gaps in our knowledge that were once vast and daunting. Beyond these floats, There are moored buoys anchored to the seafloor, continuously measuring conditions at fixed locations, and wave gliders that autonomously traverse thousands of miles, gathering data on surface conditions. Each piece of this intricate puzzle contributes to a more complete picture of the ocean's ongoing transformations. This continuous stream of data, flowing from the very heart of the ocean, allows scientists to do more than just observe. It allows them to predict. Data from the Global Ocean Observing System is crucial for improving climate models and forecasting extreme weather events. The ocean, as we've explored, is the planet's great thermostat, absorbing and redistributing vast amounts of heat. Understanding how much heat the ocean is storing, what scientists refer to as ocean heat content, is paramount to predicting future climate patterns. When the ocean releases this stored heat or shifts its currents, it can trigger phenomena like El Niño and La Niña, which dramatically influence weather patterns across continents, bringing droughts to some regions and floods to others. By meticulously tracking these oceanic shifts with GOOS, we gain a clearer foresight into these powerful natural cycles, enabling communities to prepare and adapt. It's a testament to our collective human ingenuity, turning the ocean's vastness from an impenetrable mystery into a readable, albeit still profoundly complex ledger of planetary health. But our quest to understand the ocean extends beyond its current state. It reaches deep into its past, seeking the echoes of ancient climates and forgotten worlds. Scientists use deep-sea sediment cores to reconstruct Earth's climate history, stretching back millions of years. Picture a long cylindrical tube, carefully extracted from the ocean floor, revealing layer upon layer of accumulated mud, shells, and microscopic fossils. Each layer is a page in Earth's diary, a geological record of past ocean temperatures, atmospheric carbon dioxide levels, volcanic activity, and even the types of life that thrived in ancient seas. By analyzing the chemical composition of these sediments, the oxygen isotopes in the shells of ancient foraminifera, or the pollen grains preserved within, scientists can piece together a detailed narrative of our planet's climatic fluctuations. These core samples provide invaluable context for understanding current climate change, showing us just how much the Earth's climate has naturally varied over millennia, and crucially, how unprecedented the current rate of warming and acidification truly is. It is like holding a piece of deep time in our hands, a tangible link to the planet's profound memory. As we delve into the ocean's past, we are simultaneously pushing the boundaries of discovery in the present, using techniques that were unimaginable just a few decades ago. Environmental DNA, eDNA analysis, allows scientists to detect the presence of marine species in an ecosystem by sampling and analyzing genetic material left behind in the water. Imagine being able to know what creatures inhabit a vast stretch of ocean without ever seeing them. That's the power of eDNA. Every living organism sheds genetic material, skin cells, scales, waste products, into its environment. By filtering a water sample and analyzing the DNA fragments, scientists can identify a remarkable array of species, from tiny plankton to elusive whales. This revolutionary technique is transforming biodiversity surveys, allowing for more comprehensive and less invasive monitoring, especially for rare, endangered, or hard-to-find species. It's like listening to the genetic echoes of life, revealing hidden biodiversity and providing critical insights for conservation efforts at an unprecedented scale. This molecular window into marine life extends even further, allowing us to understand the very fabric of adaptation and evolution. Marine genomics, the study of the entire genetic code of marine organisms, is revealing incredible insights into species adaptations to extreme environments and their roles in ecosystem function. From the bioluminescent creatures of the deep sea to the heat-loving microbes around hydrothermal vents, marine life has evolved astonishing strategies to survive and thrive. By sequencing their genomes, scientists can pinpoint the specific genes responsible for these adaptations. Perhaps a gene that allows a fish to withstand crushing pressure, or a microbe to metabolize sulfur in the absence of sunlight. This knowledge not only deepens our appreciation for the sheer ingenuity of life, but also holds immense potential for biotechnology and medicine, hinting at novel enzymes, proteins, and compounds that could benefit humanity. It's like reading the instruction manual for life's most extraordinary feats, written in the elegant language of DNA. While we are increasingly able to assess or, quote 18, the unseen through genetic analysis, we are also learning to, quote understand, the ocean in entirely new ways, moving beyond the mere detection of anthropogenic noise. Hydrophones, underwater microphones, are used by scientists to study the natural soundscape of the ocean, providing insights into marine animal behavior and geological processes. The ocean is not silent. It is a symphony of natural sounds. The clicks and whistles of dolphins communicating, the low rumbles of whales migrating across vast distances, the crackling of snapping shrimp, the groaning of icebergs, and even the distant echoes of underwater earthquakes and volcanic eruptions. These are all part of the ocean's natural acoustic tapestry. By deploying hydrophones in strategic locations, scientists can map migration routes, identify breeding grounds, and even detect previously unknown seismic activity. This acoustic monitoring provides a non-invasive way to observe marine life, especially in the vast, dark depths where visual observation is impossible, allowing us to understand their intricate sensory worlds and the subtle rhythms of their existence. All this intricate monitoring and understanding brings us back to one of the ocean's most fundamental and vital roles, its capacity to regulate our planet's climate. The biological pump is a critical process by which marine organisms transport carbon from the surface ocean to the deep sea, playing a major role in global carbon sequestration. Imagine the ocean's surface as a vibrant sunlit pasture. Here, microscopic phytoplankton, the grass of the sea, absorb carbon dioxide from the atmosphere through photosynthesis. When these tiny plants are eaten by zooplankton, or when they die and sink, their carbon-rich bodies and waste products begin a slow descent into the deep ocean. This continuous rain of organic matter, often called jacy, quote 21, carries carbon to the depths, where it can remain sequestered for hundreds or even thousands of years. This biological pump is an elegant natural mechanism that has helped regulate Earth's climate for eons, effectively drawing carbon out of the atmosphere and locking it away. The efficiency of this pump is profoundly influenced by ocean temperature, nutrient availability, and the health of marine ecosystems, making its continued function a cornerstone of our planet's climatic stability. As we consider these vast interconnected systems, it becomes clearer than ever that the ocean is not a collection of separate bodies of water, but a single, continuous entity. Despite being divided into named oceans, Pacific, Atlantic, Indian, Southern, Arctic, the global ocean is one continuous interconnected body of salt water. This seemingly simple fact underscores the profound interconnectedness of all marine life and all ocean processes. A pollutant released in one part of the world can eventually travel to another. Species migrate across vast basins, following currents that link distant shores. The Quote 22 of thermohaline circulation, which we touched upon earlier, is a powerful testament to this unity, moving water, heat, and nutrients around the entire planet, influencing climates and ecosystems far from its point of origin. This singular, liquid realm reminds us that the challenges facing one part of the ocean ultimately affect us all, reinforcing the need for global cooperation and a holistic approach to its stewardship. And so, as we absorb these insights, allowing the gentle current of knowledge to flow through our minds, we are once again drawn back to the profound, soothing presence of the ocean itself. The ocean's vastness and the rhythmic sounds of its waves have a documented calming effect on the human mind, reducing stress and promoting a sense of well-being. This isn't just anecdotal comfort. Scientific studies confirm what poets and philosophers have long understood. The blue spaces of the ocean, its expansive horizons, and the consistent, predictable rhythm of its tides and waves engage our senses in a way that fosters tranquility. The sheer scale of it, the endless horizon, puts our daily worries into perspective. The gentle roar of the surf, the vastness of the depths, and the knowledge of its ancient wisdom all contribute to a meditative state, inviting us to release tension and find a quiet space within ourselves. It is a profound gift, a natural balm for the soul, a reminder that even as we seek to understand its scientific intricacies, the ocean continues to offer us peace, wonder, and a deep connection to the living world. With each fact, each discovery, each technological marvel that allows us to peer deeper into its heart, our reverence for the ocean only grows. We are learning to speak its language, to read its history, and to listen to its silent, vital hum. Yet, for all we uncover, the ocean retains its enigmatic allure, a testament to its boundless complexity and its enduring power to inspire awe. We continue our journey, ever more attuned to its subtle wisdom, ever more committed to its profound protection.